Hey, I just wanted to quickly plug that if you guys want any tutoring, some new slots have opened. If you look in the description, there's a link to my physics and maths tutor profile in which I do tutoring on there. Hello everybody, welcome back to another episode of the A-Level Cookbook. Today we're going to be going through the AQA A-Level Chemistry Paper 1 from June 2019. Figure 1 shows an incomplete Born-Haber cycle for the formation of cesium iodide, and this diagram is not to scale. Table 1 gives some values of the standard enthalpy changes, and we've got the enthalpy of atomization of cesium, our first ionization of cesium, electron affinity of iodine, enthalpy of lattice formation of cesium iodide, and enthalpy of formation of cesium iodide. It says complete figure 1 by writing the formulas including state symbols of the appropriate species on the two blank lines. So with this whole topic, you need to know your definitions and the state symbols as well. If you're having to memorize the definitions, then you don't know what you're doing. And I say this in every single video, because these are crucial for coming up with mechanisms and structures and how you're going to do things. So if we look here at this top line, we're going from cesium gas plus iodine gas to something, and then all of a sudden you've got cesium gas plus and I minus plus. So the difference between here and here is that this has become positive and that has become negative. So whatever line this must be must change this one into cesium plus. So you should think in your head, okay, right, so I'm going from gaseous cesium atoms to a cesium 1 plus ion. That is the first ionization energy. So it would be cesium plus gas plus an electron plus I gas. Now here we're going from we've got cesium gas and it still stays as cesium gas, and we've got a half I2 solid becoming a half I gas. So that should ring to you that we're making 1 mole of gaseous atoms from an element in its standard state. So that's the enthalpy of atomization. Here there's no change between these two, but if you look here, we've got solid cesium iodide, and there's an arrow going down. This line here must be cesium solid plus a half I2 solid, elements in their standard states forming their this compound here. So it's always good to label this as well, just for your sakes. It's the enthalpy of formation. That's when 1 mole of a compound is made from its elements in its standard states. Here we're going from cesium to cesium gas, which is the enthalpy of atomization of cesium, and then here we're going from I2 solid to I gas. It's the enthalpy of atomization of I2. Here it's the first ionization energy. Here we're going from iodine gas, like atoms gas, to I minus gas, so that's going to be the enthalpy of electron affinity for I. And then here we're going from gaseous atoms to solid ionic lattice, so that's the lattice enthalpy of formation. It's just really important to recognize those because the definitions play a key role in what you're doing with these calculations. So then it says, use figure 1 in the data in table 1 to calculate the standard enthalpy of atomization of iodine. The enthalpy of formation is this arrow, and as long as you start and finish at the same point, so starting here and finishing here, then the enthalpy changes should be the same. So that means the enthalpy of formation is going to be minus, so let me just write these down and start again. So the enthalpy of formation of cesium iodide is minus 337, and that will equal, so the atomization of cesium, which is 79, plus the atomization of this iodine, which we don't know, so I'm going to call that X, plus the first ionization energy of cesium, which is 376. Then it's going to be the next, which is the enthalpy of the electron affinity of iodine, so minus 314. And then it's going to be the lattice enthalpy of formation, which is minus 585. So then what I'm going to do is I'm just going to tidy this up so my working out is nice and neat so that my examiner who's miserable can actually see this, because to be honest, you guys give them a hard time with all the slop you write in your answers. So I'm going to show sympathy to them and be nice and say my working out is nice and clear so that they can have a good time marking this. Minus 337 plus 444 gives you an X of plus 107. Always include the plus as well. Kilojoules per mole. There you go. The enthalpy of lattice formation for cesium iodide in table 1 is the value obtained by experiment. The value obtained by calculation from this perfect ionic model was this. Deduce what these values indicate about the bonding in cesium iodide. So if you look at the experimental value, so if we look at the experimental one, they're saying minus 585, but then they're saying the ionic model, so theoretical, is minus 582. You can see that they're quite similar, so that means it's almost perfectly ionic, or purely ionic. So just a quick revisitation of this topic. So when you're assuming something's purely ionic, you're assuming that it's a positive ion and a negative ion. They're both spherical and there's no polarizing. When you have, so this is perfectly ionic. Now when you have partial covalent character, what happens is you start to polarize the other ones, it kind of distorts it like this. So partial covalent. What happens is the electrons in the negative ion are pulled towards the positive ion. So the way I like to think of it, maybe this might not technically be correct, is that this is like saying that there is ionic plus covalent a bit of covalent bonding going on here, and this one's just ionic alone. So a lot of the time you'll find that in an experimental enthalpy change, you'll find that this is more exothermic, and the theoretical, calculated on all your bonds and stuff, is less exothermic. So what I mean by that is, like here, for example, the experimental was minus 5A5, and that's minus 5A2. Another example, maybe a bit more extreme, might be like 780 is the actual experiment, but theoretically it might have been 600. You see, that's more negative, more exothermic. The way I like to think of it is it's more exothermic, meaning you've got more bonds made, because exothermic is bonds made, and that helps me remember, well, it's, you know, ionic and a bit of covalent going on, if that makes sense. Rather than ionic, which is just one type of bond being made, ionic and covalent means you're making more bonds. Now, I don't know if that's technically correct, and any chemists might want to kill me, but like, this is how I just remember it, and it's an easier way to make sense of this. So then if you've got a larger discrepancy between this and this, it suggests that there is covalent character involved as well. Because if you see that this is more exothermic, it means that there's also that covalent character there as well, meaning that more bonds have been made, because exothermic is bonds made. And what is it? So now it says, use data from table 2 to show that this reaction is not feasible at 298 Kelvin. So here's table 2, and they've given us these entropy changes, and they've told us the temperature, and they've told us the overall entropy change here as well that we want. So delta G equals delta H minus T delta S. So list out what you have if you need to. So delta H we know is 337. We know that T is going to be 298. Delta S we do not have. Delta S is going to equal S end minus S start. We always measure changes in things by doing end minus start. So for example, if my weight now is 70 and last year was 60, you would do in your head 70 minus 60, which is the end weight minus the start, which gives you my delta weight of 10. My change in weight is 10, which means I've gained 10. Technically speaking, if I were to say, for example, I was 60 kilograms this year and 70 last year, my delta weight is 60 minus 70, which is minus 10, which means the minus means I've lost weight. But we don't really do that. We kind of just say, oh, it's 70 minus 10, and then you remember that you've lost it. So just what I mean is, what I'm trying to get at is that we always do end minus start. So the entropy at the end is going to equal, so we got to do it in terms of its molar ratios and all of that jazz as well. So at the end, we've got 82.8 plus a half 117 minus the entropy at the start, which is just 130. So if we do that, we should get 11.3 joules per Kelvin per mole. Now this formula only works if all the units are consistent, so I'm going to convert this to kilojoules. So that's going to become 11.3 times 10 to the minus 3. I'm just going to leave it like that. It's the same as saying divided by 1,000 kilojoules per Kelvin per mole. Then delta G would equal delta H, so that's going to be 337 minus 298 times delta S, which is going to be 11.3 times 10 to the minus 3. If I do that, I should get plus 333.63, which is roughly plus 334. And then you need to show that it's not feasible. Well, delta G is greater than 0, therefore it's not feasible. So time of flight mass spectrometry can be used to obtain large molecules such as the pentapeptide, this. P is ionized by electrospore ionization, and its mass spectrum is shown here. Describe the process of electrospore ionization and give an equation to represent the ionization of P in this process. In time of flight mass spectrometry, the whole point of the first step is to just make some positive ion of some sort, and then it's able to go through an electric field where it's a positive end and a negative end. If it's not charged, then it won't be accelerated, because if you put it in an electric field, it'll be accelerated towards the negative end, and it gives it more kinetic energy. Then what you do is you pass it through a field with no electric field, so it's not, going faster and moving towards any negatives. And then it hits a detector, and then you can figure out, things based, like the mass charge ratio and so forth. So the whole point of the first step is to just generate positive ions. Now they've told you here that this is electrospray ionization. It's in the name. So what you do is you dissolve P in a solvent, and then what you do is you pass it through a needle or a nozzle, you could say. So this is the spray part. And then what you do is you apply a high voltage, the electrode part. Then what happens is each P gains a proton, H+. Then what you get is this equation, which is going to be P plus H plus gives you pH+. There you go. Then it says, what is the relative molecular mass of P? So just go back and have a look. So here we can see we have a nice peak of 556. But remember, we've added an H+. So it's actually 555. So there you go. So molecule Q is ionized by electron impact in a time of flight mass spectrometer. This Q plus ion has a kinetic energy of this. The ion takes this long to reach the detector. The length of the flight tube is this. Calculate the relative molecular mass of Q, and then K equals a half mv squared, and so forth. So the amount of people that just fumble this without even thinking is just really, really weird. Look at what the questions told you, and use a bit of thinking, please. Routines never work. So number one is that they've told you, well, look at what you've been given. They've given you the time, they've given you the distance. So velocity equals distance over time, which in this case is going to be 1.5 meters divided by the time in seconds, 1.23 times 10 to the minus 5, which is going to equal 1.22 times 10 to the 5 meters per second, right? The reason I've worked that out is because Ke equals a half mv squared. That will give us what our mass of this thing is that we want. So then I can rearrange this to get 2Ke over v squared equals m. So m is going to be 2 times its kinetic energy, so it's 2 times 2.09 times 10 to the minus 15 over the velocity we just worked out, so 1.22 times 10 to the 5 squared. If we do that, we should get 2.808 times 10 to the minus 25 kilograms. This formula, and it tells you here, is in kilograms. So to convert that into grams, you times it by 1,000, which is 2.808 times 10 to the minus 22 grams. Now this is the part where people fumble really hard because they're like, oh, I've got to do mass equals mole times mR or some weird rubbish like that. Think for a second what's happening. What did you actually work the mass out of? People just sort of blindly calculate things. This is the mass of one molecule of Q. Now it's asking you to work out the relative molecular mass. All of your relative molecular masses are measured in grams per mole. So for example, carbon is 12 grams per mole. That means that every single mole of this weighs 12 grams. So if we want to figure out, this is for one molecule of it, right? So this is per molecule. We want to do it per mole. So all you do next is you would just do 2.808 times 10 to the minus 22 times Avogadro's constant. If you do that, you should get 169.06, which is roughly 169.1. Always try and follow, similar number of significant figures the question's given you, or decimal places. This question's about periodicity. The period 4 elements of their compound state the meaning of the term periodicity. So it just means that you've got repeating patterns of physical or chemical properties. So then it says identify the element in period 4 with the highest electronegativity value. So let me get a periodic table. So here, this is a period. So 1, 2, 3, 4, 5, 6. And then across, these are groups. So group 1, 2, 3, 4, 5, 6, 7, all the way up to 18. So here they want to know what's in the element in the period 4 with the highest electronegativity value. So that's 1, 2, 3, 4. So it's in this period. If it's the highest electronegativity value, it's whatever is closest to fluorine, because that's the most electronegative. So it's going to be bromine. Then it says, identify the element in period 4 with the largest atomic radius and explain your answer. Period 4 here, we need to think about what determines atomic radius. So you've got your nucleus, and then you've got lots and lots of shells of electrons around it, right? Here, because we're all in the same period, we're not adding any electron shells. So if you move across the period, the only thing that's going up is the nuclear charge. Even though you're adding electrons to the outermost shells and stuff, because the nuclear charge is higher, you're actually dragging them more in with more attraction. So as a result, generally across a period, you have an increasing atomic radius. That's why people love jumping to saying atomic radius, ionic radius, and all that jazz and not knowing what they're saying. So in this question, it's saying what's the most, the largest atomic radius. In this case, it's going to have something with a nucleus that doesn't really drag its electrons in as strongly. So it's going to be the one with the lowest nuclear charge, which is potassium. So it's potassium, and why? Well, it's exactly why I just said this. It's got the smallest nuclear charge and similar electron shielding. All of them have the same number of shells or similar. So that's why it has the largest one, because it's got the largest atomic radius, because it's got the least nuclear charge that's dragging those electrons in. Just think of it like that rather than memorizing answers. And also, whenever you're describing like atomic or ionic radius, you should really talk about the shielding to justify why you chose that. Not adding this part doesn't tell them why you've picked it, because for example, here versus iodine. Iodine has objectively got a bigger atomic radius, but it has a higher nuclear charge. So if we just said, smallest nuclear charge, we're not explaining, why it can't be iodine, why it can't be any of these other things. So it's just important to be wary of that too. So here's two reactions of arsenic oxide. Name the property of arsenic oxide that describes its ability to react in these two ways. So here is showing AS2O3 plus 6HCl makes this, and AS2O3 plus this makes this. That's an acid, that's a base. So it's able to react with an acid and a base. So it is amphoteric. Because acids react with bases, bases react with acids. So if this is acting as an acid, that's got to be acting as a base. And here, if this is acting as a base, that's got to be acting as an acid. So there you go. Now it says complete the equation for the formation of arsenic hydride. So let's have a look what's going on here. So we've got AS2O3 plus some amount of zinc plus HNO3 gives you ASH3 and zinc, ZnNO3 2 and then H2O. So to balance this, what we need to do is we need to balance our elements as best as we can first. Complete the equation for the formation of arsenic hydride. So this is a bit devious, this question, because it's arsenic hydride, so it's getting a bit funky here. So if you look at zinc, it's gone from an oxidation state of 0 to +2. So that means it's lost 2 electrons. If you look at arsenic, then you can see it's what, -6, +3, still +3 here. But if you look at the hydrogens, that's +3, that's got to be -3. So each H has gone from something to -1. If you look here, it's +1 because it's HNO3. So it's gone from +1 to -1, which means that it must have gained 2 electrons, right? In this equation, we have three H's on this side, right? So that means this equation has got to have been, originally 3 H's giving you, 3 H minuses. And each one of that's 2 electrons, so we've got 6 electrons plus this. I'm like really sketching out just a quick redox equation if you can't tell. Zinc, because it's become Zn2 plus 2E minus, right? We're gonna need 3 of these to match the electrons here. So we're gonna need 3 zincs, 3 zinc. Okay, so this next question says figure 3 shows some reactions of aqueous ions. So let's have a quick look at what's going on. So figure 3 is showing FeH2O6 3+. We're adding it with some concentrated HCl, and we've got something going on here. We're reacting it with a carbonate, we got this precipitate, and then we can do another reaction to get it down to FeH2O6 2+, and then we do some more stuff and we get a precipitate here. Fine. So then it says give the formula precipitate J and state its color, and then give an equation for reaction 1. So if you look at formula of J, we're reacting this, which is a metal aqua ion. So metal aqua ions behave a little bit differently. So these are a specific type of complex ion, and I see people get confused about this quite a bit. Any transition metal that has 6 waters can behave very funkily, one of which is acting as an acid. Now these 3+ ions, what they can do is they can form a precipitate when you react them with this when you react with the metal carbonate. So it forms a hydroxide E precipitate, CO2 and water. If it's a 2+ ion, then it will just form that metal, the carbonate. So for example, it would just form CuCO3. So it's not that this forms Fe2CO, CO3 whatever. This one's actually becoming Fe, like the OH3 thing here. So that, for example, it would become this. That's what all of the metal aqua ions that are 3+ will do with the carbonate, which is a solid, and then also as well as that, its color is brown. The equation for this then is that because it's a metal aqua ion, it can act as an acid. Anything that puts out an H+ acts as an acid. Anything that accepts an H+ is a base. So here, if we look, if you want to write whenever you're writing an equation, just look at what you already definitely know is going to be in it. We know for a fact it's going to have FeH2O6 3+ in it. And that's going to be aqueous, plus some mysterious thing, and we definitely know that we're going to be making FeOH3 H2O3 solid. So those are the two things we 100% know, right? We're going to be reacting it with Na2CO3. The Na2 is irrelevant. It's the CO3 minus that's doing the job. That's all funky. So CO3 2- is reacting with this. We know for a fact that this has gone from H2O6 to H2O3. So that means that 3 of these have lost an H. It's acted as an acid. That's how we get the OH. It's not a ligand substitution reaction. It is an acid reaction, acid-base reaction. So if this has lost H's, then those H's have to go somewhere, which has gone to here. So what you end up with is, well, you're going to make 3 H2Os because H2O3 here, 3H is gone. This is taken by some CO2s. So we're going to make 3 H2O, liquid, and we're going to be making CO2. Some of those O's are going to go into making waters. So if we have 3 H2Os and one of the oxygens are being nabbed, we're going to need 3 of CO3, to make enough waters. And then there's 3 carbons here, each with 2 oxygens left. So it's going to be 3 CO2 gas like that. So now it says give the formula of L and an equation for reaction 2. So you're getting this and you're reacting with HCl and then you get this complex ion and it's a solution. So what's happening here is you are doing a ligand substitution reaction. So you're going to have FeCl4 minus. The reason it's Cl4 is because you just can't fit as many around the central metal ion. That's why it's not FeCl6. And this is a key example you need to know as well. So then the equation for this is you've got FeH2O6 3 plus. You definitely know that's there. Always add what you definitely know. So plus something makes FeCl4 minus plus something else. Now 100% we know that it's going to be reacting to make this. So we know that there's going to be Cl4 minuses here, aqueous. And we know that all the waters that were once on here have been booted off. So we're going to have 6H2O here, liquid. And then we're going to have 4 Cl4s to match this. Sorry, not Cl4s. Cl minuses. So we're going to have 4 of them. So you can just do it like that, and that makes this a lot easier rather than sitting and memorizing like 200 equations. The bit that needs memorizing, unfortunately, is the color and the complex ion. The rest of it you can kind of fall into place. So this suggests a reagent for reaction 3. We're going from FeH2O6 3 plus to FeH2O6 2 plus. So the difference here between here and here is that this Fe must have gained an electron. So if it's gained an electron, something else needs to be oxidized. We need to add a reducing agent of some sort. The reducing agent that we can use, a very common one, is something with iodide ions in it. Now it says suggest a reagent. So you can't just say iodide ion, you need to include what it is that you would actually add. A reagent means just what are you putting in this mixture. So for example here, you can see it says Na2CO3. You can't really have CO3 2 minus ions on its own. It has to be delivered as with something else. So that's why they're adding Na2CO3. That's the reagent. The actual thing that's doing the reacting that we care about is this. So in these questions, when it says give a reagent, it's saying don't just say, oh, you reacted with H plus or I minus. What are you going to use? If you're adding an acid, you need to list a specific acid. Next it says give the formula of precipitate M and state its color. So we're adding FeH2O6 2 plus and a concentrated amount of NH3, and then we end up with a precipitate. So the precipitate has to be, well, it's got to be something to do with the Fe2 plus, right? So it's Fe2 plus, and there's going to be OHs in it, and there's going to be H2Os. General rule of thumb is that if it's got no charge left, it's going to become a precipitate in this topic. So in this case, Fe2 plus, it's going to have 2 OHs, and the rest is still H2Os, so you got 4, right? That's how you do that. And its color is going to be whatever the color of the Fe2 plus ion is, which is green. Transition metal complexes have different shapes and many show isomerism. Describe the different shapes and complexes and suggest how they show how they lead to different types of isomerism. So it says use the examples of cobalt complexes and platinum, and then you should draw the structures of the examples chosen. So you need to think about the entire levels of shapes and things and bits and bobs that you can think of. So the shapes that you can possibly make are going to be octahedral, tetrahedral, square planar, and then in terms of the isomerism you can have, it's cis-trans isomerism. So you've got to go through them one by one and draw them all out. So like shapes of molecules, you should do the same thing here. So we're going to do, first of all, I'm going to talk about the shapes of each complex one by one, and then I'm going to move on to the next bit, the isomerism, and then the optical isomerism bit as well for each of these, because these are optical. We have cis-trans, but we also have optical isomerism, which I should have mentioned here as well. Sorry, whoops. So try and format it in a logical way. So if we talk about the shapes that we can have is that with cobalt, it's CO2 plus. Well, actually, I'll put the 2 plus on the outside of the brackets. So we've got CO, and we can start with octahedral. So if we've got octahedral, you draw your, your bits and bobs and your wedges and your thises and your that's, right? And then I'm just going to use H2O. So draw the ligands like so. So start with the lone pairs, and then you can draw them like that. Anything with a lone pair can act as a ligand, because, by definition, to form a coordinate bond, you have to donate electrons. So there you go. This is really badly drawn. Just pretend that's not there. There's 2 plus. So you need to explain as well, describe the types and show how they lead to different types of isomerism. We also need to describe how they actually exist to begin with. So as well as that, here we have 6 coordinate bonds, and that's octahedral as well. Cool. So then next we could do tetrahedral, so we could have CO, and then we could have like one ligand that can't fit around them as much, so Cl minus. So remember, Cl minus is massive compared to the one, so you can only fit 4 around it like this. The overall charge of this is going to be 2 minus. That's got 4 coordinate bonds. So that's 4 coordinate bonds. That's going to be what, a tetrahedral. Whoops. So we've done octahedral, we've done tetrahedral. Now we need to do square planar. So with square planar, you've got 4 coordinate bonds, and it's with platinum. So with platinum, you could have, I'm going to use NH3. Oops, let's do it dotted, sorry. NH3, and then H3N, H3N, cool. And that is square planar, which we've just said. So I've dealt with the types of shapes. So we've talked about shapes. Now we need to talk about isomerism, and we need to give examples. So if we look at the first type, if I look at these octahedral complexes, so I'll start with optical isomerism, and this happens when you have a bidentate ligand. Now, if you want, just literally, make up whatever you want that has, it is bidentate. So you need to have two lone pairs. One example is ethane diamine, so H2N. There's a carbon, there's another carbon. And then an NH2 here, and there's your lone pairs. That's a bidentate ligand. So then when you have this, the way I draw these is I always start by drawing the metal ion, and then add the draw it lone pair by lone pair. Optical isomerism, you should also define what it means. Is you've got non-superimposable mirror images. So if you put your right hand over your left, they're not the same, they don't match. That's non-superimposable. So here we've got our CO as our central metal ion, and then we'll draw your dashes and your wedges and all that stuff out first, and then you can add it lone pair by lone pair. And I'll do it here as well. And you also get, two enantiomers we should really add. So then lone pair, NH2. This is going to be a really crooked diagram. Let me move that somewhere else. NH2, and then you just connect them. So there. Lone pair, and H2N, NH2. It's always easier to try and put the nitrogens nice and separate, so you can draw big, long, very obvious skeletal bonds formulae bonds like that. So NH2, NH2, lone pair, like this. There you go. So that's one of them, and then the mirror line, you just draw them the opposite way around. Again, lone pair by lone pair. So then here, I've got NH2 this way, and then H2N like this. There. Then NH2, NH2, this. Then we have NH2, NH2, this. So you can see those are mirror images of each other. So that's one of them done and dusted. We've talked about octahedral optical isomerism. We need to talk about octahedral cis-trans isomerism. So an example could be where you have two different ligands to the others. So you would have cobalt. So let me just draw the bits out. And then another cobalt ion here. And if we say, let's say we swapped some of the H2s with NH3s, for example. So NH3, OH2, H2O, H2O, like that. So this would be your trans isomer. Your cis isomer is when they're next to each other, the two odd ones out. So NH2, NH3, NH3, OH2, 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 OH2. So that's your cis isomer. It's always easy to draw the lone pair bit first and the rest. So we've done octahedral, we've done its cis and trans isomers. Now we need to do tetrahedral. Do we know any structures to do with that? Not massively. Right, so there we go, that one's out. Then square planar, we have cis and trans isomerism in the square planar complexes as well. And the key example we should probably pick is cisplatin. So cisplatin is square planar and has cis-trans isomerism. So then the cisplatin is PT. If I just draw the wedges out, because I always do it like this, and the dashes, and then another PT here, there. So cis is on the same side, so NH3, H3N, and then Cl, and then the opposite side, so H3N, NH3, Cl. So that's your cisplatin, and then that's your trans isomer as well. There you go. So like transplatin, I guess we would call it. Transplatin. So then we've dealt with the optical isomerism in octahedral complexes, cis-trans isomerism in octahedral complexes. We talked about tetrahedral, talked about cis-square planar and the optical isomerism and cis-trans isomerism in that. If you do it systematically like that, step by step, you will literally just never miss anything out. So that's done and dusted. Okay, so this question is about group 7 compound. Solid sodium chloride reacts with concentrated sulfuric acid. Give an equation for this reaction and then state the role of the sulfuric acid in this reaction. So unfortunately, it's those reduction reactions you kind of have to memorize, but all of them start off with Na in your halide, so Cl in this case, plus H2SO4 makes NaHSO4 plus HCl. All of them start off with that, and then the other ones go further down in the steps, so they'll reduce it eventually down to H2S. So here, the way I remember it is that Cl can only go as far as this, Br can reduce this down to SO2, and then iodine can go all the way down to H2S. So HSO4. So that's how I remember it. Cl, Br, I. So that's only going to be Bri. Well, I minus, I should really say all of these. And then H2S is only I minus. If I kind of remember that and then like kind of make the equation up like based on everything else in there and fill it out. So here, the question's also asking you, what's the role of the sulfuric acid in this reaction? So if you look at what's happening to sulfuric acid, it's going SO4, still SO4, but it's lost an H. So anything that loses an H is immediately a proton donor, which means it's an acid as well. Now it says fumes of sulfur dioxide are formed when sodium bromide reacts with concentrated sulfuric acid. For this reaction, give an equation, state one other observation, and then state the role of the sulfuric acid. So in this case, they've told you that you're reacting. So always write what you know objectively is happening here. So we've been told that we're reacting sodium bromide. We know that we're going to be reacting it with sulfuric acid. And they've told you that you're making fumes of SO2 by default. The rest of this then forms, well, we're going to make something else happen as well at the same time. So one of the things we're definitely going to make is water. Because you can see that's lost H2s and it's become SO2. So one of them is going to be water. Because I've got nowhere else to put it. It's not like HBI in this case. So what else have we got left? We've got SO2, H2SO4, H2, and then NABR. The NABR's got to go somewhere. Well, the BR becomes BR2. That's another thing that we end up making. So then the only other option is we're going to have Na put with something. So it's going to be Na2SO4. These are one of the ones you have to memorize, unfortunately, but like there's kind of ways to remember bits of it. So balancing these out, balancing those out, there we go. So that's balanced, done. It says what observation you would see, so we can see that we are going to be making Br2 gas, so it's going to be, you're going to be making a brown gas. Then it says here, what role is the sulfuric acid acting as? So we need to look at the oxidation states of all of these because I can see we're making Br gas. That goes from -1 to 0. So if that's happening, this is being oxidized and this is being reduced. So the role of the sulfuric acid is that it's reducing something, it's reducing itself but oxidizing something else. So it is an oxidizing agent. Chlorine reacts with hot aqueous sodium hydroxide as shown in this reaction. Give the oxidation state of chloride in NaClO3 and NaCl. So +1, -1, -1, +1, -6. It's got to be +5. The previous question told us that Cl2 then, becomes something with a +5 oxidation state and a -1. So from 0 to +5 it's oxidized, 0 to -1 is reduced. So it has been oxidized and it's been reduced. So solution Y contains two different negative ions. A sample of solution Y has been put in a test tube and we've added silver nitrate, an excess of dilute nitric acid, and then finally an excess of concentrated ammonia, and the observations after each of them are recorded in this table. So it says give the formulas of D and F and give an ion equation to form the formation of E, and then give an equation to show the conversion of D into G. So if we add silver nitrate, what we end up making is a cream precipitate containing D and E. It's a mysterious sample, and they've added silver nitrate and it makes a cream precipitate. So by default, that first one has to be AgBr. Now here, it's told you that we add excess dilute nitric acid, and you get a cream precipitate, and then you get bubbles of gas of F, right? So if we do that, so look back at the steps. They added silver nitrate, the first step. Then they added the nitric acid. Then they added the ammonia. So the first step made something, like a compound D, which is here, and then some mysterious E thing. Now when you add the nitric acid, D is unchanged, but now you get this gas F. So this E thing must have led to this gas F. Now bubbling in gas generally means the release of CO2 in these kinds of experiments. And also we add the nitric acid to remove carbonates, to remove false positives, because it can form a precipitate as well. So that means that E has to be a carbonate of silver. So Ag is Ag+, it's CO3 2-, so it's going to be Ag2CO3. Then it says they've added excess concentrated ammonia solution, and then you get a colorless solution containing this complex ion G. So then that has to be, well, you've got AgBr plus NH3. You definitely know those are the two things that are being added. So then it tells you making a cream precipitate and this and that, blah, 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 right? So we've sorted that part. And then this is bubbles of gas F. The gas F has to be CO2. So we know that this is the ionic equation to form E, which we know is now Ag2CO3. So that means we have, well, it's ionic, so we're going to look at what's changed. So we know that we have Ag plus, and we're adding something to it, and we're making the compound E. So it's eventually making Ag2CO3, and that's the solid. So the only other ion that can go here has got to be CO3 2 minus, which means it's got to be 2 Ag here. That's that. Then it says the equation to show the conversion of D into G. So if you look at D, that's the cream precipitate, remember, and it's just an equation of ionic, so we're fine here. So it's AgBr. And we know that they're adding ammonia. So start with filling out the equation with what you know is being added and made, and then you can do the rest and add in the bits and bobs. So it's made a colorless solution, so it's not going to make Br2 because that would make a brown liquidy thing. So here it has to be Br minus on this side, no matter what. Otherwise it would be brown. So then what's left is that we've got AgBr becoming this, right? There's a Br minus lost here, and we know we're making a complex ion. So the equation that this actually becomes is Ag NH3 2 plus, and this is one of these examples that you want to know as well, that, and we're adding 2 NH3s there. So that's the equation there. A student does an experiment to determine the percentage of copper in an alloy, and if you've seen my other videos, you could tell that I complain about this a lot. There's no way to do this other than reading the question and using reading comprehension. If you absolutely do not know what to do, then work out moles blindly, fine, and you might get some method marks. However, if you're going for the home run, there is no way to do this other than just reading the question and making sense of what's happening. So each step you should be thinking, what's reacting with what? Why do I care about this sentence? Because every sentence here has its use. A student does an experiment to determine the percentage of copper in an alloy. What they do is they get 985 mg of this alloy, and they react it with nitric acid to get a solution, and it tells you in the question all of those give you copper 2 plus ions. So then you get Cu 2 plus ions, right? Then what they do is they make it up to 250 centimeters cubed. Cool. Shakes the flask thoroughly, and then what they do is they take 25 centimeters cubed of the Cu2 plus mixture and do what with it? So they take it to conical flask, and then they add excess Ki. And it says, then what they did is with this this mixture is, they then use exactly this much thiosulfate. So they add Na2S2O3, and we know its volume and its concentration of 9 and 0.808. And it says in the question, it reacts with all the iodine produced. So why are they telling you that? Go back and think about it. It's excess Ki, eventually that makes I2. So then it says calculate the percentage of copper by mass in this alloy, and give you answers to a significant number of significant figures. The equations are here. Look at them and think about which way they link to which step. If I call that number 2, that's here. If I call that number 1, that's here. So now it makes sense what you need to do. You can use this, the S2O3, to work out how much iodine was made from the previous bit. All of the iodine that was made must have come from the Ki, the I minus, reacting with this. So everything that was actually this, I2, must have come from all of that reacting. So we can work out the moles of this, and then we can go back up here like this. So you need to use the steps like that, otherwise you'll just fumble every question like this. And people say, oh, I hate back titrations and this and that. There's no set method for it. It's just reading the dang question, dude. So the general rule of thumb is, if you're going to work out the moles of something, be able to justify to yourself why you're doing it while working out this stuff and practicing it for yourself. So if you could do that, you know what you're doing. If you can't, then you don't know. So I'm going to work out the moles of the S2O3 2 minus, because I know it comes from here, and it tells me in the question it reacts with I2, and I know that came from the previous step. So that's going to be its concentration, so 9 over 1,000 times, volume times its concentration, which is 7.20 times 10 to the minus 4. Therefore, I also know that all of this has reacted with all the iodine, so I know that the moles of iodine has to be a half, which all came from here. So moles of I2 is going to equal a half times your answer. But then I could see here, this iodine from here came from here, which reacted with the 2 Cu2 plus. So the moles of Cu2 plus is actually your answer times a half times 2 again, so it's the same as this. So that's going to equal 7.20 times 10 to the minus 4. And this is the moles of the Cu2 plus in 25 centimeters cubed, because it's at this step here. So that means to work out the moles of the Cu2 plus in 250, it's going to equal your answer times 10, which is going to be 7.20 times 10 to the minus 3 moles. All of that Cu2 plus in 250 has told you, it's literally told you in the alloy, all of it's reacted with that, so all of that came from this alloy. So then we know that all of these moles is going to be the copper. So we know now we could work out mass by doing mass equals moles times MR to work out how much copper was in that original thing. So 7.20 times 10 to the minus 3 is the moles times its MR, which is, 63.5, which gives you 0.457 grams. Now, therefore, they've told you that this is 985 grams of alloy. So the mass of the alloy is going to be, I'm going to change that to grams. It says 0.985 grams. So then what you would do is you'd work out the percentage copper in this thing by mass, 0.457 grams of copper over 0.985 grams of alloy times 100, which is 46.4%. If you do it like this, you'll never fumble it unless you put the wrong numbers in your calculator. If you absolutely can't do this, then fine, fair enough. Then you can blindly work out moles, but like, you know, if you follow it step by step and just think what's reacting with what each step, it's actually not that hard. Now it says suggest 2 ways that the student can reduce the percentage uncertainty in the measurement of this. So if you've seen my other videos, I'll yap about this real quick. So percentage uncertainty is equal to your uncertainty over your measured value, right? Now, how are we going to reduce this, they say? So the obvious thing is to reduce the uncertainty in your equipment. But the question says we're using the same equipment, so this is staying constant. So the only thing we can do is change this. Now this will go down if I increase this, right? So if I half this, remember that this is this all over 2. So if I, sorry, not half this. If I double this, then this will go down by half. An example would be, let's say I measured your height and you're 170 centimeters. Just choosing 170 because it looks like a pretty normal number. And then I use a really, really rubbish ruler that's plus or minus like 10 centimeters. That means the range of the uncertainty can go spread as far as 160 to 180. That's not very good. Whereas, if for some reason you were 170,000,000 centimeters tall, but I still use the same ruler, it's going to be 169,999,990, or could be 170,000,010, which you could see the effect of that is not as big. You know, the spread of it is not as big as this. So that means it's the same principle here. If we take a really big measured value, as long as the uncertainty will stay the same, so we can actually, like, you know, that would lower the percentage uncertainty if we use the same equipment. So in that, what that means in this question then is you need to state 2 ways that this student could reduce it. So you can't just say generally. You've got to actually go and look at, in this example, what they could do to try and do that. So look at what they're measuring. So it's the measurement of the volume of the sodium thiosulfate. So we want to try and make the thiosulfate volume go higher. What we need to do is, 1, we could use more alloy, because eventually it will need more of this to react. And 2, we could just dilute this, so you need a higher volume of it. Because if you just use really, really diluted this, then, you know, like, remember that N equals CV. If I really, really dilute this, drop the concentration, you keep the moles the same, I'll have to increase the volume to, you know, counteract that. So that's what you would say, both of those things. So 1 is to use more alloy to increase the volume needed of the S2 or whatever. And then also, as well as that, you could use a lower concentration of the thiosulfate. I'm too lazy, I'll just write Na2S2O3, like that. There you go. Now it says state the role of iodine in the reaction with the thiosulfate. So go back to this step and have a look. It says iodine in the question, which is I2, not the I minus. So I2 becomes I minus, right? So that means it's gone from 0 to -1. So this means it's been reduced. Where something is reduced, the other thing has to be oxidized. You can't have one without the other. If you have a half equation, you can, because it shows the electrons. This is a whole combined equation, so it means that something's been reduced, something else has been oxidized. So if this has been reduced, this has been oxidized, but it's saying what the role of this thing is. It's causing something else to be oxidized and it itself being reduced, meaning it's an oxidizing agent. Now it says give the full electric configuration of a Cu2 plus ion. So just as a general rule, this is period 1, period 2, period 3, period 4, period 5, period 6. This is S block, this is your D block, that's your P block, right? So if I wanted to jump, for example, to work out what sulfur is, I know it's going to be, well, it's in 3s and it's in the P block, so it's going to be 3P, and then it's going to be what? 1, 2, 3, 4. So 3P4 is the outermost one. So you can use that here. The only difficult part, though, is the D block elements aren't, although they're in period 4, they end with blah 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 4s to 3d whatever, because the 4s fills first. That's what puts it in that period 4. So if we're looking at copper, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. Now you would think it would be 4s2, 3d, 9, but copper and chromium behave differently, and that this one prefers a 3d5, that one prefers a 3d10. So it's going to be blah 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 4s1, 3d10. This would rather give up one of the electrons, so these are all filled entirely. In this case, though, they're saying what a Cu2 plus ion is. So we remember 4s fills and empties first, so that means we're going to have 4s0, 3d9. So then it would just be 1s2, 2s2, 2p6, 3s2, 3p6, and then I always do 4s here, but you can keep it as, you don't have to put 4s0 because it's empty, and then 3d9. Cool. Now it tells you copper 1 iodide is a white solid, explain why. So there's two ways to approach this. Number one is to look at the previous question and realize it's hinting at this. Or two, if you look at an object, let's say for example, let's like blue, right? A blue object. What's coming to your eyes is blue light. And if you're supplying this whole thing with white light, what's coming back is blue. This means that this object that's blue is absorbing everything, all light, except blue. And is reflecting blue back to you. So it's reflecting blue, right? And if this is white, it means that we're putting white light on it, and all that light's coming back. None of it's being absorbed. So no, wavelengths of light are absorbed. But that's weird because copper is a transition metal. So if it's not absorbing, the light and giving you a nice color of blue or whatever, what's going on? It needs to come back to what your definition and understanding of a transition metal is. A transition metal is where you form stable ions with an incomplete d subshell. Not just not an incomplete d subshell, because objectively we've just said here a C2. Remember that copper would have been 3d10, which is not that doesn't keep that, right? So it has to be something to do with it not behaving as a transition metal anymore. So look back to, just think logically. So copper is 4s1 3d10, right? So if it's 4s1 3d10 and it's copper 1, 4s empties first. So it's going to actually be 4s0 3d10. What do you notice about that? Whoa, the d subshell is full. And that makes sense, because if the d subshell is full, there's no energy for it to absorb and then, excite the electrons and so forth. So it comes back as white. It just reflects it all. So that's exactly what you would say, is that its d subshell is filled, therefore no, wavelengths of light absorbed by electrons to excite them. And there you go. Sometimes the previous questions can give you a hint as to where it's going, or also you can just kind of think of it like, think of it as in like, do I usually think copper does this? Why is it behaving like that? And there you go. Now it says iodine vaporizes easily. Calculate the volume in centimeters cubed that this occupies at these values. The gas constant is here. So we're going to use PV equals nRT, and we're going to rearrange this to get P. So V equals nRT over P. You should really not write numbers blindly with no working out. You must write all your working out. Otherwise, what method marks are you going to get? Your examiner is not going to be asked reading your rubbish, trashy handwriting that looked like a 6-year-old who puts crayons up their nose, right? All right. So please just do that. Please, it's just so hard to read some people's handwriting, and also then on top of it trying to make sense of their working out. They've got to get through like 8 million exam papers in a day to mark, so they're not going to look at yours and be like, oh, I think that's a mark for them, tee-hee. Like, no, right? So then what you do is with all of these is list out what you have. So PV equals nRT only works for a specific gas in a specific circumstance. So the moles here would be moles of a gas or multiple gases, because every gas in the universe ideally behaves on this way. So here we're going to list out what we have, but we don't have volume. That's what we want. We know it's R. We know that's 8.31. The temperature has to be in Kelvin, so we're going to have to do 185 plus 273, which is what, 458. And then we know it's pressure, but it has to be in base units. It can't be kilopascals, it has to be just pascals, so 100,000. This is a volume in meters cubed. So PV equals nRT uses base units, right? So like we don't use centimeters, we just use meters. So then we need to work out the moles of this gas. Well, they've told us that it's 5 grams. So we know that the mass is going to be 5, and its MR, so moles is going to be mass over MR, right? Now this is I2 gas. Right, I2. So we're going to have to do 253.8, which is 0.0197 moles. Just don't slip up on that part as well. So then, if we put the numbers in, we get V equals 0.0197 times the R, which is 8.31, times the temperature 458 over 100,000. Which if we do that, we get 7.50 times 10 to the minus 4 meters cubed. But the question wants centimeters cubed. So the way I think of it is that 1 meter is 100 centimeters. So if we're going from 1 meter to 100 centimeters, you're timesing by 100. So 1 meter squared would be 100 with 2 zeros. Here, squared, because you're going to do times 100 squared. Because if you think about it, 100 by 100 lengthwise, well now it's squaring this, 100 by 100 is going to be that. So then 1 meter cubed, well if you're cubing this, you're going to cube what you're timesing it by, so times 100 cubed, which could be 100, 2 more zeros, centimeters cubed. So here we've worked out this in meters cubed, so what we need to do is we need to times that by 10 to the 6, with 6 zeros. If we do that, we get 750 centimeters cubed. There you go. Sulfur trioxide decomposes on heating to form this equilibrium mixture. Here, a sample of sulfur trioxide was heated to and allowed to reach equilibrium. The equilibrium mixture contained this much sulfur dioxide. Calculate the mass of oxygen in this equilibrium mixture. So the rule is you need to write out what's just happening to yourself so you know what's going on. So what I mean by that is you would do initial moles, you change, and your equilibrium moles or volume or gas or whatever, right? So initially, they've told you that there was a sample of something and it was heated, right? We don't know what it is. However, this is when it's just before it's hit equilibrium, So if there's no equilibrium to begin with, there's none of these two made, because this will go down as these go up. So you would write 0 for each. But they've told us here that the equilibrium mixture had this much sulfur dioxide. So we need to work out the moles of sulfur dioxide, which is going to be 6.08 divided by its MR, which is 64.1, which is 0.0949. Now, every one of these, so every two of these makes two of these, but one of those. So if this has gone up by from 0 to this will have gone up by 0.0949 over 2. We would have added that. So therefore, the moles of oxygen at equilibrium is going to be 0.0474. They want you to find out the mass of it. So the mass is going to be moles times MR, which is going to be 0.0474 times the 32, which if you do that gives you 1.52 grams. I know that the whole steps weren't necessary in this case, but writing it forces you to follow a logical sequence of steps. Now it says a different mass of sulfur trioxide is heated and was allowed to reach equilibrium in this. The amounts of each substance are shown here. For this reaction, the equilibrium constant was this. Calculate the mole fraction of each substance. Whoops. And then it says calculate the expression for Kp and then calculate the total pressure of this. So we need to do a bunch of steps. So luckily here, they've already told us the moles of everything at equilibrium nicely for us, which is 2.12. If you do that, you get 0.32 over 2.12. You get 0.15. And then you would just rinse and repeat for the other ones for each one of the moles. So if I just skip ahead, that's 0.57, and then that's 0.28. Then it says to write out what Kp is. So Kp, remember, depends on what these are, and it's all to do with partial pressures. So it's going to be your products. It's going to be the partial pressure of SO2 all squared times the partial pressure of O2 all divided by the SO3 squared. So the partial pressure of SO3 squared. Now we've only worked out the mole fractions. Partial pressure equals the mole fraction times the total pressure. So then, just if I do a side bit here, the partial pressures for all of these is going to be mole fraction times the total pressure, which is... we haven't been told. Fine. That's okay, because I'm going to just leave it as in terms of algebra anyway, and see what happens. If you're in doubt and you're stuck, just try doing it in that way, and maybe you can get something out of this. And put the numbers in that you know. So here, it's 7.62 times 10 to the 5 equals the partial pressure of SO2 squared. So the SO2 was 0.57. I'm going to call the total pressure just P, big P. So it would be 0.57 big P all squared times the partial pressure of O2, which is going to be 0.28. It's mole fraction times the total pressure here. So that's going to be the SO3, which is 0.15 P squared. So then it will get 7.62 times 10 to the 5 equals, and if I just tidy this up, I'm going to multiply out the brackets and expand and whatever. 0.090972 P is P squared times P cubed, all divided by 0.0225 P squared. So these P squareds and P cubes cancel out. So we get just, why have I written P twice? So you get P to the 1, right? So and then if I just tidy this up, so I'm dividing this number by this, and it's going to be something P, right? So it's going to be 7.62 times 10 to the 5 equals these two times the P. So if I do that, get 4.0432 P. So then P, the total pressure, would be 7.62 times 10 to the 5 divided by the answer we just worked out, which is 188,464.5 And what did they actually want us to work out? They just wanted to work out, the total pressure. So then we're going to try and stick to the number of significant figures they've given us, so 1.88, and I'm going to do times 10 to the 5, times 10 to the 5, so I'm going to do it in standard form. So 1.88 times 10 to the 5. There you go. Now it says, for this reaction at 1050K, the equilibrium constant is this, and then for this, it's this. And it says, explain how this information could deduce the forward reaction is endothermic. So the question's told you this, but you can also just have a look at yourself as well. So if we increase the temperature, what's happened to Kp? If we increase the temperature, that's given us a higher Kp. If we decrease the temperature, we have a lower Kp. Alright? Now, Le Chatelier's principle says that whatever you do to an equilibrium, it will counteract the change. Now, loads of people like writing counteract the change, but don't actually say by how. So if I increase an equilibrium's temperature, the equilibrium will shift to decrease that temperature, right? So if increasing the temperature led to this, right, what it's saying is that I've increased the temperature, the equilibrium has shifted to decrease the temperature, and by doing that shift, it's actually made Kp higher. Now, if we look at Kp is this over this. So if the Kp value is higher, there's more of this, meaning that decreasing the temperature means my equilibrium shifted that way. So, sorry, not decreasing, increasing the temperature has made my equilibrium shift that way, sorry. So if my equilibrium wants to shift this way after I've increased the temperature and it wants to lower the temperature, it must mean it's endothermic to absorb and take in that extra heat. So you would just write that. So here then, it would be that Kp higher with higher temperature, therefore, you know, it means the equilibrium shifted to the right with the higher temperature, so it's endothermic in the forward direction. There you go. So you can just, again, there's a reason why they tell you, oh, Le Chatelier's principle is this, because you should use it. So then it says, use the data from this question to calculate the value of Kp at 500K for the equilibrium represented by this equation. So they've told you to use the data from this question from before, right? Now they've told you these two things, and they've told you it's for this temperature here. So the Kp at this temperature was, for this previous question, 3.94 times 10 to the 4, right? And this is for this Kp expression, wherever it's gone, from the previous part. Wherever we ended up doing it, somewhere, right? Now they've told you that this is the equation, and this is our previous equation. So you can see that this equation and this equation, you've times this by a half, right? Kp was all of this stuff fumbled around, but now our new Kp is going to be SO2, the partial pressure of SO2, times the partial pressure of O2 to the half, all over the partial pressure of SO3 now, versus whatever this thing here. So you need to compare them side by side, what's happened. So this has gone from a squared down to nothing, so it's square rooted. This has gone to a square to nothing, that's square rooted. This has gone down to nothing, this is square rooted. So what's actually happened is this Kp, the entire expression, is the square root of this thing. So then, if Kp is equal to all of this, we have the same temperature, and the original one here was that, the new Kp is going to be the square root of 3.94 times 10 to the 4, because we square rooted this whole thing. So that's, I've seen this come up a couple times, just be careful, like not to get caught out by that, and look at it carefully. So it's 198.5, 198.5, and then also as well as that, it's asking for the units. So the units of the first one they've told you was pascals. We've square rooted it, so it's going to be Pa to the half. There you go. Square rooting is putting the indices to a half. So if you see that, it means square root. If I do 2 to the half, that's the same as saying the square root of 2. If you ever have a negative, it means 1 over whatever it is. So 2 to the minus 1 is 1 over 2. So if I do 2 to the minus half, it's going to be 1 over the square root of 2. There you go. Now it says this question's about structure and bonding. Draw a diagram of the strongest type of interaction between these two molecules of ethanol. So let's just draw a quick sketch of what that is. So it's C2H5, and then there's an O, and then there is an H, right? And there's lone pairs on this O, and this is delta negative, and that's delta positive. The OH here should signal to you that there's hydrogen bonds going on here. So then go lone pair, lone pair, lone pair, lone pair, slight negative. H is slightly positive, slight positive. And your hydrogen bond is between this delta positive hydrogen and the lone pair of an oxygen. There you go. Now it says methoxymethane is an isomer of ethanol. Table 5 shows the boiling points of these things. In terms of intermolecular forces, explain the differences in boiling points. So ethanol has a higher boiling point, whereas methoxymethane does not. So then, it must be that we'll compare them side by side. The only difference between the two of them is that there is no OHs in this and no hydrogen bonds. So therefore, ethanol has a higher boiling point. Why? Because it has hydrogen bonds, and why? Because they're strongest between molecule force, therefore lots of energy required to overcome, you know, the usual. But that still doesn't tell us why it's higher. Methoxymethane only has van der Waals forces and permanent dipole-dipole. Therefore, less energy is needed to overcome. Therefore, you know you've got a lower boiling point. There you go. That's all. Now it says draw the shape of the POCO3 molecule and the shape of the ClF4 minus molecule. Include any lone pairs that might influence the shapes. And then in this, the oxygen atom is attached by a double bond that uses 2 electrons from the phosphorus. Name each shape. So in this case, just draw like the start. So phosphorus is in group 5. So it's going to have 1, 2, 3, 4, 5 in its outer shell. Right? And it's told you that there's a double bond and it uses 2 electrons from the phosphorus with the oxygen, like this, here. And then it's also told you what Cl3, so there's a Cl, 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 each one of them has a single bond like that. So if I draw that in terms of it just without all of this stuff going on, it would be P double bond O, Cl, 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 right? Now here you can treat the double bond as one when you're deciding its shape. So there's 1, 2, 3, 4 bonding, 0 lone pairs, because remember we can treat the double bond as a single, so that means it is tetrahedral. Then, if we look at ClF4, so Cl is in, what's Cl? It's in group 7, so that's 1, 2, 3, 4, 5, 6, 7. And it's told you that it's got 4 Fs on it, so there's a covalent bond with the F, there's a covalent bond with the F, there's a covalent bond with an F, there's a covalent bond with an F. However, it's also told you it's ClF4 minus, so there's an extra electron here, right? So then we have 1, 2, 3, 4 bonding pairs and 2 lone pairs. So the shape that you have is going to be square planar. So if I draw that as what it's supposed to actually look like, so whenever you're deciding shapes, I always do it like that. Cl, F, 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 F. There's a lone pair, lone pair, lone pair, lone pair. So that's what it is, and the shape is going to be there, square planar, and its angle is 90 degrees. So this question is about different pH values for pure water at 40 degrees C. The pH is this. The student thought the water was acidic. Explain why they're incorrect and determine the value of Kw at this temperature. So any pH is dependent entirely on H+. And it's not just how much H+ there is, it's also its proportion to everything else. This is pure water, so there's only H+ and OH- in it. When you have pure water, what it is that H+ and OH- are equal. So then it becomes Kw equals H+ squared, right? Or H- squared. So then here, well, I mean, first of all, to just deduce why they're incorrect, H+ equals OH- in pure water. And then it's asking you to work out Kw, so it would be Kw equals H+ squared. So the H+, they've told you, the pH is that, so it's going to be 10 to the minus 6.67 squared. If I do that, we get 4.57 times 10 to the minus 14. There you go. So sodium hydroxide was added gradually from a burette to this much propanoic acid, and they measure the pH at regular intervals, and there's a result. So you can see that the pH is starting at 3, it's kind of going up, and then slowly, and then eventually get that nice big sharp jump where we get our lovely equivalence point and so forth. So let's use this figure to determine the Ka of this, right? So Ka, you have two options. It's H+ squared over HA, or it's H+ times A minus over HA. Now, you need to remember that this A minus is salt, because an equilibrium for weak acid is so far to the left, they're practically the same. So if you have a weak acid and, weak acid plus the salt, then it's going to be this one, or if it's on its own, it's this. So there's two ways of going around this. I know that here, the pH of this acid on its own is, so the pH of acid only is going to be 3. And I also know its concentration, HA, is going to be 0.08. So then Ka is going to be, so H+, it's going to be 10 to the minus 3 all squared over HA, which is 0.08. And if you do that, you get 1.25 times 10 to the minus 5. That's one way. The other way is a bit more big brainy. So we need to look carefully at what's going on. So at the equivalence point, all the HA is neutralized. So at the equivalence point, whatever this volume is, blah, 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 or whatever, right, that will tell you how much NaOH is needed to neutralize this thing. Now, if we think about it this way, if we go halfway to the equivalence point, so the half equivalence point, let's have a look what happens. So at your half equivalence point, think about it logically. H+ is whatever, fine, right? But then we said at the start there's no A-. So at half equivalence point we have some amount of A- made, right? But this will have reacted with the OH- to make the salt. So that will have dropped by however much. This will have dropped by however much. Now, HA plus base makes salt plus water. If this has dropped by a half, this will have gone up by a half. Right? So we have a half of this, but all the half went here. So that means that this A minus is equal to HA at this half equivalence point. So therefore, at this point, KA would equal H plus A minus over HA. But those are the same. Can you see how those cancel out? So KA is H plus at that point. So then, if we look at where this half equivalence point is, so it's half of this, and this is a quick read off, it's like, what, 19 and a half here, so it's going to be 9.25-ish, which is kind of around this area. If you read it properly and you get it, then you should get a volume of, whatever, like 9 point something, and then you read across and you get the pH there. The pH at that point is about, what, 4.95-ish? So that means Ka is going to equal 10 to the 4.95, the pH at the half equivalence point, which if you do that gives you 1.26 times 10 to the minus 5. Either is fine. One thing to remember, if you want to take a fact from this to memorize, for a monoprotic acid, the half equivalence point, where half of all of this acid's been neutralized, A minus equals HA, so then this equals this. There you go. It says suggest which indicator is best for this. So then the indicator, you want it to change where you've had a slight amount of acid or base and it changes suddenly, right? So we want it to change within the equivalence point range from here to here. So imagine this is where like your half equivalence is, right? We want it so that it changes really fast, even if you had the teeniest amount above. Whichever one fits this range and is most narrow is the best option. So then if we have a Luke, what options we have, the one that fits this range best, so that's 3 point, that's too low. That's still not very great. That's like from here to here. 8.2 to 9.8. It's kind of like that. That's pretty good. And then what, 11 to 13? Not great. So it's going to be that one. Right, so a student prepared a buffer solution by adding this much of a salt to this much solution and then mixed it thoroughly. Then they added this much potassium hydroxide, and then it says calculate the pH. So whenever we're working with pH, we are going to eventually need to find not equals, but we're going to eventually need H plus, right? And we need to look at which of the formulae we are going to use. We know Kw, we know Kas, we know all this other stuff, right? So we need to think about what's going on in this mixture. In this mixture, we're probably going to be using Ka, and it's going to be H plus and A minus over HA. Why? Because here they've told you that it's a weak acid mixed with its salt, and it is an acidic buffer too. So an acidic buffer by definition is a weak acid mixed with its salt, and A minus is salt. Whenever you do a buffers question, it's always, I think, the best thing to do is to write HA plus OH minus gives you a salt, so that's what, A minus plus H2O, and label it to yourself if you need to. So that's an acid plus a base makes a salt and water, right? And then what you do is you logically work through it. So it's the initial moles of everything, your change in moles, just like equilibria, because this is an equilibria thing, your end moles of everything, and then in this case we're going to need our end concentrations. So do it step by step like that and you'll never fumble it. I know that it's not very clear cut, but if you do it bit by bit, it makes sense. Initial moles is when they first mix together everything and it's not done any reacting yet. So let's look at what we know. So the student prepared a buffer by adding this much salt to this much of a weak acid and mixed thoroughly. So I know for this case, I know the amount of salt at the start here is 0.0136. Often it's 0, but here they've physically put salt in. Now, the weak acid is that. So the moles of the acid is going to be, whatever mysterious acid this is, 100 over 1,000 times 0.05. If I do that, I get 0.5. 0.5 times 100 over 1,000 gives you 0.05 moles. So just to tidy that up, I'm going to just get rid of that and put 0.05 moles here. So 0.05 moles. Cool. In this exact scenario, think about it, there is no OH. 0. Right? However, the student then adds this. Right? So you need to think about, remember that I said this is, the initial moles is everything that's put together but not actually reacted yet. Right? So in this sentence, what that means is there's going to have 3 times 10 to the minus 4 moles of this base. Think about what's going to happen logically. This isn't going to fancy having base around. So this is going to react with this. They're going to drop and we're going to get more of this. So then think about it this way. This is 3 times 10 to the minus 4, which is 0.0003. Right? So there's much less of that compared to this. So what's going to happen is these two are going to react and this is going to drop. So then what this is this is going to eventually be 0. So the change in this is minus 3 times 10 to the minus 4. It's a monoprotic acid, so they act in a 1-to-1 ratio. So that's going to drop by minus 3 times 10 to the minus 4. If these two have dropped, these two go up. I don't really care about water. It's not in the Ka equation. So that means the moles here, sorry I made a mistake in my calculation, is 0.0139. Now we need to work out the end concentrations. The volume they've told us is 100 centimeters cubed. They've not added any extra fluid or any water to this. So that means it's going to be 0.0497 divided by 100 over 1,000. And then the same for this. And you'll end up with an end concentration of 0.497 for you and then 0.139 for you. So then we've got the new concentration of the acid, the new concentration of the salt, which is what we need to do Ka with this, because that's what it says. We rearrange Ka, so Ka times Ha would equal H plus times A minus. If I divide that by A minus, that gives you H plus. So write your working out, please, then put the numbers in. So H plus is going to equal 1.41 times 10 to the minus 5 times RHA, which is 0.497 over 0.139. If we do that, we get 5.0415 times 10 to the minus 5. So then pH is going to be negative log to base 10, blah, 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 right? So if I do that, negative log to the base 10 of my answer, I get 4.297, but they want it to 2 decimal places, which is roughly 4.30. There you go. So even though, yeah, I didn't have to do some, like, I just think this is the best way to do it. Any acids-base buffer question, anything that's reacting two things together, and it's like, this happened and then this happened, it just makes the most sense to do it this way. Then you don't screw up anything unless you put the numbers in wrong. A buffer solution has a constant pH, even when you dilute it. Use a mathematical expression to explain this. So the buffer solution, the only thing that links pH right is H+. Cool. Ka equals H plus A minus over HA. So let's rearrange that to get the H+, so we can see if we can do some maths to figure that part out. So Ka times HA, right, would equal these two times together. So if I divide that by A minus, I get H+. Now, it's talking about when you dilute it, so you're changing the volumes, right? So H+ is dependent on these two. K is constant. H+ is proportional to HA over A minus, right? Now, if I wanted to rewrite this even further, I could say that this is proportional to the moles of HA divided by its volume, which you can also write like this, all over the volume divided, so the moles of HA over the volume of A minus, the moles of A minus, sorry, divided by its volume. You can see how those cancel out, and it's entirely irrelevant as long as the volume of the whole system stays the same. So therefore, this ratio between the two of them, or the fraction, stays constant. So then, you would say H+ is constant, and if H+ is constant, pH is constant. There you go. Thank you very much. I hope that helped. Please like, share, and subscribe. You know the drill.